And up next, it is my great pleasure to introduce KIPAC fellow Sanskriti Das. And Sanskriti is going to be telling us about feeding and feedback in the gaseous halos of galaxies. So take it away, Sanskriti.
Hello, everyone. My name is Sanskriti. I am a postdoc fellow at KIPAC, and I have been working on the circumgalactic medium, or the CGM, of spiral galaxies. CGM is basically the multiphase gaseous halo that surrounds the stars and the interstellar medium of galaxies, and is expected to be, extended out to the virial radius of galaxies. Although the definition of galaxies kind of vary from people to people. For the optical people, maybe the disk is the whole galaxy, while, from a hydrodynamic point of view, the whole galaxy is anything within the virial radius. So it is more like intragalactic medium, but we'll just stick to the whatever it is called in the literature. And as you can see, there are, inflowing accreting gas and outflowing gas and also recycling gas. So all these gas flows are crucial to the galaxy formation. And so we expect the CGM to also play an important role in galaxy evolution. However, as the surface brightness of CGM is really low, it is extremely challenging to detect the signals from the CGM. And the CGM also has a rich multiphase structure with its density and temperature, both spanning more than 3 orders of magnitude range. And I study 2 extreme phases of the CGM. I study the cold neutral phase, which is somewhere, slightly below the 10,000 Kelvin gas, using radio telescopes where we probe the 21 centimeter emission. And I also study the hot ionized gas using X-ray emission absorption and millimeter. Now, the main reason we are interested in the circumgalactic neutral hydrogen is because a lot of accreting gas is missing. Since H1 is the raw fuel of star formation, we expect the H1 accretion rate to be as large as or larger than the star formation rate. But in nearby galaxies, the H1 accretion rate is almost an order of magnitude lower than the star formation rate, which kind of sounds unphysical. And that implies there has to be a lot of hydrogen, neutral hydrogen, in the CGM that is actively accreting to the disk of the H1. And we use deep stare techniques to look for the H1 or the 21 centimeter emission from the CGM. And we use both single dish and interferometers to make sure we can probe both the clumpy H1 as well as the diffuse H1. And we actually reach almost 2 orders of magnitude better sensitivity than previous mappings. So that really allows us to look for very faint H1 emission. And so far, we have been able to detect H1 around only 2 Milky Way-like galaxies. Here, I'm just showing one because qualitatively, they look pretty much similar. In the left, you can see the detections at different pointings out to almost, 75% of the R500. And in the right-hand side, you can see the column density as a function of radius and also the velocity. So the H1 is co-rotating with the disk out to almost 100 kiloparsec. And along the minor axis, it is inflowing, which is totally as is expected. And now we are expanding it to now less massive galaxies where the accretion mode and efficiency is expected to be different. But we'll see what happens when we have the data. Now moving to the other side of the phase, that is the hot CGM. This is the most massive and volume filling phase, which is expected to have all the missing baryons and metals that are missing from the stars and interstellar medium. And also galactic feedback is supposed to dump a lot of energy and momentum in the CGM, although we don't know if it has any observable effect in individual galaxies. Now, there are 2 ways we can study is X-ray and millimeter. In millimeter, one of the very common techniques is cross-correlating the Compton-Y maps with the galaxy catalog. That has been done before in more massive halos. But in low mass halos, the challenge is that they are smaller and also fainter. So you have to stack a lot of galaxies. And by lot, I mean like 500,000 galaxies. And here we found that the thermal energy and baryon fraction in these galaxies are significantly different from predictions, implying that the feedback mechanism and the source is maybe different from what is predicted in the simulations. And now moving to the last, but definitely not the least, probably the most important and also most difficult part of the hot CGM analysis. So we can study the hot CGM both using X-ray emission as well as absorption. But one of the main challenges is that the emission is dominated by the soft X-ray foreground and background that accounts for more than 95% of the total emission. So it's literally like a needle in a haystack problem. And also the foreground is, it is anisotropic, it varies with time, it has a very complex spectroscopic shape that you can probably see in the right-hand side. So during my PhD, I spent most of the time studying the Milky Way CGM that actually is like the omnipresent foreground in the soft X-ray. And we found a supervirial 10 million Kelvin gas coexisting with the virial phase that also has a non-trivial chemical composition. There have been a lot of follow-up papers after that. So in every paper, we're just finding something new, which just makes life more complicated than solving, but it is what it is. And when it comes to external galaxies, things are even more challenging because now Milky Way CGM is also part of the background. And in the right-hand side, you can see just one spectrum. This is the only external galaxies with a detected CGM where the, little difference between the gray solid and the dashed line is the detection. And here in the bottom left, you can see the first detection in X-ray absorption from an external galaxy. So obviously 1 is not impressive, but it is still better than 0. So that is encouraging. And, we are now looking for more galaxies to see how it varies as a function of mass and star formation rate. And I'll just end up with the update that last year we got around 450 kilosecond of XMM Newton time. And the data just came a few weeks ago in the last month, actually. So very excited to see what happens there.
Okay, thank you, Sanskriti. Any questions? Roger. If we have the microphone, we can capture it on Zoom.
Just a very nice talk, but a quick comment. Just come on, me do this. The ionized part of the intergalactic medium and of galaxies both can be measured using dispersion measures from fast radio bursts. And that's going to get a lot better pretty fast. It's very good so far. It was a former Stanford undergraduate who first, did the work on this. But it's that's a sort of complement of these investigations, yes. And I think it's going to get better a lot.
Yeah, actually, I mean, we have also worked on FRBs, and one of the issues with FRB is that it probes the whole electron dispersion, not like phase-wise different dispersion. While in X-ray, we can also probe like a specific temperature. So maybe with, combining both X-ray and FRB would be better to see what is coming just from the hot phase and what is coming from the total. So
they're doing that too. So that's
right. Yeah.
One question I had actually, I'd be interested to know your perspectives on when we're talking about studying the hot CGM with X-rays, the role that the microcalorimeter sensors like on XRISM and Athena and future missions will play versus what you can do with gratings, and what your thoughts are on that.
Well, that's a great question, and yeah. So I think it's hard for me to choose between microcalorimeters and gratings. One of the main limitations now is the lack of spectral resolution. As you know, like CCDs practically don't have any spectral resolution, and microcalorimeters are going to change that significantly. However, one of the differences between gratings and microcalorimeter is that at higher energy, microcalorimeters are better, while at higher wavelengths, gratings are better in terms of spectral resolution. So I would prefer to have both in the same time, to have, a broadband spectral analysis. And also, since I work on both absorption and emission, a lot of absorption sightlines look much better in grating, not only in terms of spectral resolution, but also you can have, complementary information from absorption and emission, because they both have their pros and cons in terms of like fundamental physics, not just the instrument you are using.
Okay, great. That's good to know. Thanks. Any last questions for Sanskriti? Yes, Irina.
Awesome work. I have a quick question about the H1 co-rotation maps, and I was wondering if you either observe this in your data already, if there's a cutoff to where the co-rotation stops, or if there was such a cutoff, if you'd be able to detect it with your data.
That's an interesting question, but till now we don't really see any cutoff. So all the pointings you are seeing, if I can point, maybe what is happening? Yeah. So
gets absorbed, unfortunately, in the
anyway.
screen.
So yeah, in the right hand side here, you can see all the black points, the black field points. So these are the points along the major axis. And we have observed only up to this, and we see the co-rotation kind of continues. So it's hard to say if it still continues beyond that or not. But we don't really have any kind of expectation of continuing co-rotation or stopping it. So yeah.
Okay. In some of my work with like cosmic ray pressure supported halos, we do see extended co-rotation in that region, and so we would predict like at some point there'd be a drop off in the rotation curve, but I can talk to you more about that.
Yeah, sure.
offline.
Yeah.
Thanks.
The only limitation right now is that, I mean, we can do this with single dish, but we always need the single dish and interferometers together to compare what is diffuse versus what is clumpy. And right now there is no existing interferometer map that goes beyond this radius. So first we need to have that, and that is more expensive in terms of exposure time than single dishes. So that's the only limitation now.
I see. Well, thanks.
Hey, well, let's thank Sanskriti again.